I'm Julian Brown. I'm an incoming PhD student in aeroastro at MIT. I'm here on behalf of NPS, so on the second row here, specifically the Space Systems Academic Group. Today, I'd like to present my vision for the future for CubeSats. What I envision is that the 5th grade class of the next generation will be launching satellites. So towards that end, I want to make space as inexpensive as possible. And one of the biggest limiting factors on that is the cost of a ground station. So today I'll be showing you how to build a $3,000 ground station. So the motivation behind this is that for all these different applications, small sats, CubeSats, high-altitude balloon testing, all this requires multiple ground stations. Each one probably has their own different communication modulation scheme and frequency. And for each of those, you need your own little box, little black box that demodulates it. Well, what I want to switch over to is a single ground station, which is powered by a software-defined radio. And this is what one of those looks like. So there's an antenna there, which probably has a power amplifier attached to it. But the part I'm concerned about is here, the laptop SDR combo. So first of all, what exactly is an SDR? Probably preaching to the choir here. You all know what it is. But I'm kind of dumb, right? I'm an incoming PhD student. So this is what an SDR means to me. It's just a local oscillator multiplied with an input signal. And this can work one of two ways, right? It can either have the signal at RF and then move it down to baseband, or it can take the signal at baseband and move it up to RF. This is what a software-defined radio looks like. This is specifically the EDIS USRP N210, and it costs less than $2,000. So with another $1,000, you can buy a pretty good gaming laptop and hook it up to this. What is GNU Radio? GNU Radio is an open source toolkit for radio frequency communications. It wraps C++ or C code with Python. So it's both easy to use and the signal processing is done in a very powerful language. This is what a very simple GNU Radio block looks like. This is probably the first setup you'll have when you're first testing out the radio, testing out your USRP N210 and your radio. So over here we have a USRP source, which is powered by the UHD block, which is the USRP hardware driver. And this block does all the hard lifting for communicating with that USRP N210 I showed earlier. Basically what this outputs here is a complex signal. So that means it takes samples and it shows you IQ samples coming out here, and then it pipes it into whatever you have next. So the variables here are 5 megahertz for the sampling rate. That means 5 million samples a second. And a center frequency, which tells you 1 gigahertz. That's the frequency I'm going to be transmitting or receiving at. In this case, since it's a source, that means it's receiving at that frequency. And I'm directly piping that into a frequency sink, which should show me something like this when there's no signal present. So you can see it's down at negative 120 dB, so this is the noise floor for the system I was using. When I transmit with the radio, I get a nice little spike there. So this is a very quick, easy demo to show that your setup's working. Next up, you'll probably build something like this, which is a full-scale ground station. It might take you a few weeks, but this one took me about 6 months, I think, 2 10-week internships over the summers. And I'll be going through each of the components of this today. You'll be seeing this a lot, so don't worry about taking pictures too quickly. You'll have plenty of time to look at it. So first up is this section, which is the combo of the USRP source, which I already explained, and something called a power squelch block. So the power squelch block makes this able to operate continuously. Basically what this does is as a cutoff threshold, and if the signal power is above that threshold, then it'll pass it on. It'll pass on data points. So it gates. So that means that if the power is below that, it doesn't send anything onwards. So if you don't have any signal, you don't do any signal processing. The next part is a normalizing block. And so what this consists of is a root mean square block, which takes the running average, converts it back from a float to a complex so you can divide the original signal by it. So very simple. This just brings your IQ samples back to the region from 0 to 2, from -2 up to +2. The next section is how you do Doppler correction. In here, we've got a little signal source, which is just a cosine wave. And the reason we use cosine instead of sine is if you have a zero frequency one, then you'd be multiplying your signal by zero. So you want to multiply by 1 instead when you have no Doppler correction. This one specifically, I'm using a Doppler correction of 2 kilohertz. You can actually plug a negative number in here and it will shift it in the other direction. So you can actively update this block. So if you look over on the left side here, it's kind of hard to see. There's a single block here called an XML RPC server. And that gives you access to the variable here called Doppler externally. So you can command that from some other Python script or just anything that has a socket connection. And you can tell it to update that Doppler value, and it will change the Doppler shift in here. So that can be corrected in real time. Over here we have our first demodulation section. So first up, there's a rational resampler. So I mentioned earlier that we were using a sample rate of 5 megahertz. So 5 million samples per second. That translates directly into bandwidth. That means we have 5 megahertz of bandwidth. If our sample rate needs to be slightly different for use in other blocks, like these over here, then we can use something called a rational resampler. So I'm just changing it from a sample rate of 5 million here to a sample rate of 4 million. That's all this block does. Over here we have the GFSK demod blocks. So this allows us to, in real time, demodulate 2 signals simultaneously. So that means we can be listening in on 2 slightly different data rates at the same frequency simultaneously. And if either of them has data showing up, then one of these blocks will spit something out. They'll say, here's your data. The samples per symbol here tells you how many samples of the 4 million per second you need until you get some data. So 40 samples would be a single bit for GFSK, because that encodes a single bit per sample, which means that this one's operating at a data rate of 100,000 kilobaud, or 100 kilobaud. And this one here is 200 samples per symbol, which means it's operating at 20 kilobaud. So let's take a closer look at what's in this GFSK demod block. This is actually a hierarchical block in GNU Radio, which is used for formatting purposes. It makes it look nice. And if you want to duplicate blocks like I have here, then it makes it very convenient. So here's what's inside of the GFSK demod block. We have the pad source, which just connects it back to the original flow graph. Another rational resampler, which downsamples it some more for use in the clock recovery, because clock recovery doesn't really like having a whole ton of samples. So we just want 5 per symbol. Quadrature demodulation just tells you where the center of the frequency is. So this will output a float that's +1 if it's slightly above the center frequency, and -1 or some other value that's negative if it's slightly below the center frequency. So that basically tells you for GFSK, is this a 1 or a 0? Clock recovery will figure out where the spacings are between the 1s and 0s. So you don't need an external clock source, right? Standard GFSK. You need to tell where the 1s and 0s are from looking at the signal. So this handles that automatically. Binary slicer actually converts it into bits. So what this outputs is those values between -2 and +2 approximately. And so you need the binary slicer to actually convert the values below 0 into 0s and the values above 0 into 1s. From there, because this outputs bytes with a single bit inside of them, you need to repack them so that they're more efficiently packed together. And then we pass that on to our Python script here, which is also built into GNU Radio. So this is all just 3 GNU Radio scripts, the 2 hierarchical blocks, and then the 1 main block. So this is actually native to GNU Radio. You can open one of these Python blocks and edit it. So I've inserted all of my ground station parsing code into this block in GNU Radio. And so this would do things like defecking, de-whitening, sync word detection, deframing, all the typical stuff you want in your ground station. So moving back to the outer block, we'll move on to the next section. This here is kind of a special section that I made specifically for our purpose. This is buffering. So what we do first here is we multiply by 64. And the reason for this is we've already normalized the signal to between -2 and +2. So some of you may recognize that should put us in the region for characters, right? Negative 128 up to 128. So then we convert it to a character. So this is just for compression purposes. The blue squares you see here represent complex waveforms, which means it's an IQ signal represented as floats, which is 4 bytes. And that's incredibly inefficient if you want to do buffering. So we first convert it to characters, which is a single byte each. So instead of 8 bytes per sample, it's now 2 bytes. And then I've got my own special little Python buffer block here, which can hold up to 4 gigabytes because my computer had a decent amount of RAM. And so this will pull in as many symbols as it can, and then only output as many as the rest of it can handle. So this limits the rest of the flow graph from tying up the reception. So this is important if you have a particularly slow computer and a very high data rate you need to be parsing at. So it allows you to run in real time if you have a fast computer, and it allows you to work if you have a slow computer. So then you convert it back to complex waveforms, so the rest of the signal processing section. And here I'm just dividing by 64 again to renormalize. The last section here in the receive is the OQPSK demodulation. So we've got 2 different modulation schemes going on in this flow graph, right? We have GFSK, and then we have a much more complicated offset quadrature phase shift keying. And we actually have 3 different data rates being processed simultaneously. So that's a total of 5 different data rates / modulation schemes being simultaneously processed in real time. And if any of them receive data, then they will output the information to whatever external server or file you have. So the samples per symbol on these, if you recall, we were sampling at 5 megasamples per second, down converted to 4. So that means that this one's operating at 1 megabaud, which is, so I've changed these values for this presentation, but we were operating in our actual system at slightly above this. So we're getting better than 1 megabaud in our downlink. And then this one would be 250, and this one would be 100. So let's take a closer look at what's inside of the OQPSK demodulation block. Once again, we have the pad source, which just connects it back to the main flow graph. We have another resampler, which is meant to downsample it to 4 for use in the next block, because it doesn't like a lot of samples per symbol. So the MPSK receiver here is just a general purpose block for phase shift keying demodulation. This does all of the terrible work of figuring out phase lock looping, all those just horrible things that you would have to implement by hand. So this is all taken care of by the toolbox. And it actually handles OQPSK, which is kind of surprising. They just mentioned in passing. So this should work with QPSK and probably with OQPSK, but we haven't tested it. And so I did, and it does work, and it's fantastic. So you pass that on. The one problem with this is it outputs a diamond instead of a nice square. So we actually have to rotate that by multiplying it by 1 plus ij for use in the constellation decoder, which takes in squares, not diamonds. So that was a bit of an oversight by the GNU radio team. But it still works, just have this one little block extra in there. And so then we pass that on to the repacking bits. Because it's QPSK, it has 2 bits per symbol, which means we have a 2 here, 2 bits per input byte instead of 1, like we had in the GFSK block. And then once again, we have our own little Python parsing script, which does all of that hard work of defecting, de-whitening, deframing, all that stuff. So then back onto the main flow graph again. Next up is TX, and we're actually doing that in the same flow graph. So this is the same USRP, so that means it's a full duplex connection. And so what this looks like is we have our little Python script at the beginning this time, and so this does the fecking, whitening, and all that, the opposite of the downlink section, passes on those bits to the GFSK modulation block. And so this has 20 samples per symbol. So that means for each input bit you shove in here, it'll output 20 IQ samples. So since we're operating at 20 kilobaud, that means we're getting 400 kilosamples per second. We multiply that by a small number, and the reason for this is you don't want your output to interfere with your input. So if you transmit at too high of a power with a USRP, then it'll actually interfere with your receive. So we want a small number here, and we'll do amplification later and system later on, so that doesn't actually matter. As long as you're getting some decent signal out, then your PA will pick up on it. And then we have our USRP sync here, which has a transmit frequency. In this case, it's 700 megahertz, and the bandwidth is just determined by how many samples per symbol you have going in. So that was 20 times 20, so 400 kilobaud, or in this case, kilohertz. So in conclusion, what we've constructed here is a briefcase-sized, very inexpensive, so less than $3,000 full duplex communication system that is completely modular, so you can pull apart pieces and insert new ones. It's very versatile for the same reason, and above all, it's incredibly simple. All of this was done by an intern, not even a PhD student, over the course of 2 summers, right? And it works in real time, which for the application we were using, we didn't have a real-time system working. Before, we were just receiving and immediately dumping to a file and post-processing with C code. Yes? So,
what version of Python are you using?
I believe it's 2.7.
Is that upward compatible with 3.3?
I'm not sure if GNU Radio likes using Python 3, but it's possible to construct code that works in both 2.7 and 3.
Do you make your source code available to the public?
Well, that depends. I'm pretty sure we aren't going to be, but...
In terms of your Doppler shift correction, do you externally have a way of controlling that, like through gpredict or something?
Yeah, so gpredict, you could output samples from that and pipe it into, it's an XML RPC server, so that just means it's a socket connection. So you need the computer, the ground station computer's IP address. That was the way I implemented it. You have the ground station computer's IP address and then the port number, which in our case was 8082. And you would command it, you would say set _ Doppler, and then a number.
So does that adjust the LO, or is it adjusting it?
So, right, there's actually 2 LOs going on here. So one is in the USRP, right? That has a local oscillator, which is the big one, right? It goes from 1 gigahertz down to 0. And we have another like smaller local oscillator here. This is kind of what we're generating with this signal source. And that one just does like a few kilohertz of shift, which is what you need for Doppler correction.
If you extend the same capability using similar demodulator kind of things, would you be willing to speculate on what an upper bound on data rate might be? You could using a laptop in this version of GNU.
An upper bound on data rate. Really, the limiting factors would be the USRP N210 or whatever USRP you're using, and the speed of your computer. The actual downlinking could be done very quickly, right? Because I had a buffer block in there. So that buffer block here, at 4 gigabytes with the sample rate we're using for this, can hold about 10 minutes worth of data. So if you wanted to scale this up and you didn't have a very fast computer to run this, then you could just increase your buffer size and you could handle whatever data rate, and it would just limit it from being real time to within an hour of your pass that you would get all the data out. I would say currently with with Ethernet and connection to the USRP and the buffer size of a USRP, you would be limited to at most maybe 20 megabaud, like just with the system I had. But there isn't really a limit to
What
this.
sets the upper bound on the sample rate you can achieve?
The upper bound on the sample rate in here would either be the speed of your computer
Yeah.
or the speed of the USRP. So in this case, the USRP's upper bound on the sample rate was, I believe, 100 megasamples.
Okay. That's really important.
Yeah, very high number. Yes?
You mentioned about receiving, so how about transmitting?
Yeah, so actually the bottom block here that I talked about last, that is transmit. So the upper part, the entire upper section here is the receive. It's much more complicated because all the big work is being done in this GFSK TX block and then the GFSK mod. So yeah, this is the transmit. So you're doing both simultaneously. Yeah.
How much output power can the USRP?
The USRP, definitely less than a watt. It's not very high. So you would probably want a PA before your antenna. if you're talking to a satellite. If you're talking, across the street, then it should be fine.
I got a dumb question. A lot of your parameters, multiply by constant 1 m, is that 1 million? What's the m?
One milli. So
1
point
milli.
zero zero one. Right. So I should explain those. So the m's are the capital M's are megas, the k's are kilos, and the m's are millis. Right. So this would be 1/64, so 15 milli.